Thank you, Dr. Bharadwaj. Good afternoon to all of you. First of all, let me say I am honored to have been invited here and to address a nice August gathering, experts of mariners, operators, shipping, and many other things which I know only in a peripheral way, because I am basically a naval architect and I deal with ships. I have been teaching, I have been conducting, consulting, and delivering a lot of projects to the industries, and of course research is part of the bread and butter part of our life in IIT. So now, humble is a taboo word, so that I will not use. But still the fact remains that being in the IIT system, when we come to take up the challenges of meeting our clients' requirements and investigations, the knowledge that it brings, and what I always say is, it is always an interaction between the client and the consultant, that we are both learning and growing, and that learning and growing process really makes us feel humble, so I cannot avoid using that word. And in that sense, we begin to know how little we know, and it's always good to say, I don't know. So this is the most important thing I do in IIT, to tell my students I don't know, because then we go back and learn, and we don't try to hide behind statements. Okay, with that very little introduction, all that I'm going to do today, the theme of this symposium here is research and its impact, and how it has a bearing to the, not only the solutions of the problems that the industry has, but how it is naturally a process which must be built in for the larger growth of the nation, for the sake of self-confidence of the nation, self-belief. So towards that, I am going to highlight a few things. Now let me get started. Okay, so that's it. Research and its impact on shipbuilding sector. And the theme of this seminar here is taking the quantum leap, promoting research and development. Now, it will be a little bit like a 2020 match, that you are going to see many facets, as we have heard from Jagmeet Makar. He gave a nice global perspective, and Ashok Muller now dwelt upon the wonderful manual that is evolved for the training purpose. And now I am going to talk of a little bit of the real intrinsic hardcore investigations we carry out for the industry. But you can look at it, as I said, like a 2020 match, enjoy and see what I'm going to show here in some brief video clippings, because I thought that will convey best what I want to. And at the end, for summing up, I will tell what I feel, how research should be interspersed with the normal growth, and what we need to do and need to continue to do. So in my outline, I'm going to do 2 or 3 case studies, time permitting, and I hope it will fit within 20 minutes. I will do my best to do that. I will then touch upon the national scenario of research and maybe sum it with the conclusions. So the case studies I have taken, it's important to emphasize that these are all very international projects. I picked the projects where we have international clients from very developed nations and dealing with very real problems. The problems happen to be, because these are very recent, just concluded, or some are still ongoing projects, which are related to the FPSO, that is the floating production storage offtake system, the large ships that are there in the production fields, tapping oil from the bottom and doing some primary processing and then sending them off in motherships to destinations. So, let me get on to the first case. What do you do? Okay, yeah. The first one is how we have simulated the stern pull-out. The ship is operational in the Gulf of Mexico, and there is the tower yoke mooring system, as you can see in the picture on the right, where it shows on a tower which is fixed there, and then you have the pendant and the mooring arrangement. And the Gulf of Mexico is a place prone to hurricanes, so anytime rough weather can set in, heavy weather, which can endanger both the yoke as well as the ship, so it has to get out of there. So to do that, this system which is operational, the owners, I will of course avoid mentioning who the owners etc., but as I said, that is it, and they wanted to simulate, is it possible to pull it out by using the ship's engine power, because this ship has an engine about 18,000 kilowatts, and whether the propeller will be able to generate enough astern thrust. Now, how do you do that? This could be done on model scale, which becomes quite complex to do in a towing tank. The other way is to use the modern tool, what we call CFD, Computational Fluid Dynamics. I'm sure all of you are aware of it. It's a wonderful tool that has evolved over the last 25 years. But the important thing to understand is how to be able to use a tool, because very often it happens that you may be giving wrong inputs, you may be making so many assumptions which are wrong, there are so many simplifications or approximations which are brought in, because honestly it is a complex set of equations it solves, and it is mind-boggling numbers in terms of millions of cells and hours of running in the computer. So it is not to be thought of as simply an animation coming out. It is hard number crunching after several days of running, which produces the results which also need validation. So what we are showing here, I just want to describe the basics. This particular ship is in 30 meters water depth, and because of weather vaning, it will always orient itself to the line of least resistance from the wind and the waves. And the mooring assembly connects the ship to the tower, and that needs to be detached, and the detachment comes by asserting the astern pull, which, if it is strong enough, in this case it is calculated to be 70 tons. So if 70 tons of astern pull can be obtained from the propeller within the available engine power, then it can detach. So we are simulating that. This is simply the example of what that weather vaning means, or I'm sure all of you know it. As the wind blows from one side, the ship will orient itself. Okay? So that's what will naturally happen. But when it goes beyond a limit, we have to do the astern pull out. Yeah. So this is the modeling part of it. I'm just showing the very superficial things in the simulation, as we call it. So here you have the size and form of the ship, and you need to simulate each and every detail there. In this case, you can see besides the rudder, there is the propeller and there is the Mavis duct. The Mavis duct is a device which will actually homogenize the flow to the propeller and therefore improve its efficiency. So all these have to be simulated, and next what is done is, this is what comes out of the number crunching. So typically there I have given, of course we use these what are called commercial Reynolds number average Navier-Stokes equation solvers. The method used I have put there. There is a complexity of making the propeller turn there within the domain, as we call the sliding mesh. The millions of cells that are used, just the description of the system where it uses 6 cores. In fact, people use even 100 core processor these days. And for one velocity simulation, astern pull, it could take as high as 86 hours. So it is the result of that that you see here at the bottom of how, as the propeller rotates in the mode, the flow takes place, and then you derive the thrust out of it. Now this is simply to say what are the results coming out of that, and as I said, we have just delivered these results to the client, and we have verified that it is possible to do it, and it is simply an example of how a very complex problem could be resolved. And mind you, to handle these programs, to reach a validation stage, to have a degree of reliability, it takes months and sometimes years. This particular project we have been doing for the past few months, But what I mean is it requires a lot of experience, insight, so that somebody can trust the numbers that you give. So it's just one aspect of how industry and academia or research institutes need to work together. They are the experts in handling the ship. We, again, with humility, have the knowledge of the fundamentals to be able to resolve the problem. And this is the very basic aspect that one has to keep in mind when we talk of research. I say this because on an average in India, research is usually taken to be something useless. I say this because people think, oh, he is doing some research. You know, and I understand why they say so, because they feel what is tangible and what is being done is the real thing, the other thing is all in the mind and in the paper. Maybe at higher levels it is not thought so, because this has again an effect on the way we look at it in India. I say this in India because I think it is going with the theme of what we are talking about, that we need to cultivate a true understanding, of course, a belief, and a kind of respect and mutual respect, that we learn to solve our problems, and therefore research is not something very exotic or high level meant only for a certain level of people. No, the research could be generated almost everywhere, every shipyard, every design process. So I'm just trying to bring out that as an example here, right? So this graph only shows that at a propeller RPM of approximately 55, this particular engine, the propeller absorbing 14,000 kilowatts of power can deliver the 70 tons of push or bollard push to pull the ship out. This is a second case study I am going to quickly. It is simply recreating the dynamic scenario of another FPSO, which is somewhere in the South American waters. And the problem, I will say the problem because it's a functioning FPSO, and I'll tell you the problem as I describe. These descriptions I will bring in when I show you the pictures. Yeah. So this is what we have actually physically done. Now this is not simulation, this is physical simulation. In what we call the wave basin facility, a laboratory conditioned system where we recreate the sea, and where of course the ship has to be made to a model scale. In this case the model is as long as 5 meters, because the ship is a 330,000 ton displacement vessel, and it has a beam of 58 meters, the depth is 30 meters, the draft is 23 meters. So you are seeing the freeboard here, which is representative of 7 meters. So you have to understand the problem here. What you see on the side of the ship on the red structures, that is what is called the risers for taking the oil from the bottom. So this ship has a peculiar arrangement that the risers are on the side, and there is what is called the riser porch on the below portion and the riser gallery on the upper portion. So all these structures are being subjected to the vagaries of the sea, and it is their experience that many of them are getting damaged or thrown out. So therefore this study came out of the necessity to be able to understand and find out the forces, the pressures that they are subjected to when these big waves come and run up on the deck and have impact pressure on those elements there, so that the design can be handled correctly. So, and you can see the maze of wires and the number of instruments that have been used. There are more than 20 transducers, a number of pressure transducers, a number of load cells, a number of what we call the run-up probes to measure how much water is rising over the deck every time the big waves splash. And this is an actual event taking place there all the time. There are also requirements that when the ship is out there, you have to have what is called a soft mooring system. So I will not describe more of that. That means it allows the ship to execute its oscillations, and this system will not interfere with the natural period with which these oscillations occur. So it should not be invasive. it should still be able to keep the ship in position, otherwise it will drift away from there, and that is not the realistic solution to it. Okay. So here is the video which shows the actual generation of waves of sea state 5 or 6 or whatever, because we do that in the computer controlled mode, that we generate the waves, and you can see how the waves get tossed up. Of course, this is a model so that the period will not relate to the period, but there is a way of scaling it up, what we call Fruit's law, etc. But let us not bother about that here now. What we need to see is that in such a condition, every time a wave is getting tossed up, it means a few meters high waves go over the deck. And therefore the dynamic pressure can be as high as 12 to 15 bar. You can imagine that is the impact with which it slams on the structure, and that is also why many of them were getting damaged and thrown around. So if the experiments are carried out well with due diligence, and the preparation of the model is something which takes months, because it is supposed to simulate exactly the way the ship behaves. That means your mass distribution, your mass moment of inertia characteristics, your GM, all these things, and also the most important deck structures, all these have to be simulated, because they are all going to play a part in the results that you are going to get out of it. Yeah. Here are some of the results, just typical to show. You can see how the pressure shoots up. All those vertical lines are momentary high peaks of pressure. That means at an instant of time, there is a very high pressure peak, and the right side lower bottom figure here, it just shows that although it looks like a single peak, there is a high peak and then it quickly descends to low value. So the question is, can you really design for this 15 bar pressure there? Then if you go by structural principles, you will have to have very high scantlings. I can only say this is analogous to if somebody gives you a slap. Momentarily you are going to face a high pressure, but that didn't kill you. But still, there is a possibility that the structure can take that pressure momentarily. So the design principles are therefore different. What is the average pressure you get over the period, and therefore can it sustain? Because otherwise it becomes impossible to design the structure if you report this is the pressure you are getting. You understand? So there are a lot more of ramifications in these things, but the interesting thing is this experiment gave us wonderful insight into something which we ourselves did not expect. But the most important is these tests are a replication of something which was already done in some European tanks, and our client did not have the confidence that that was exactly right, which is why they have come to us. So therefore we take it as an honor and a challenge that we were able to replicate that, and they are happy with the kind of results that are being verified and validated in our facilities. So that is one of the biggest gains, I would say, from these kinds of projects and exposures. Not only our own self-belief, but also the belief of others in us that we can carry out high-level jobs with a degree of reliability. This is again because it is a following C, so we had to recreate the C conditions in head C, beam C, oblique C, following C, so many things. So it's just to show what happens, and depending on the orientation, you could have severe slamming in the aft region, in the bow region, and sometimes at the middle region also, as you can see, it's happening here. So you can imagine that when you enlarge it to the real ship scenario, how frightening it could be. It's a very phenomenon that we are actually creating there. So I just want to tell you, now that you have seen this video, just what were the salient conclusions that we could gather out of this. Of course, the high dynamic pressures, the significant amount of shipping of green water that does occur in the structure, which obviously cannot be modeled by the mathematical tools that we have in hand. Because even CFD with this two media, that is air-water interface, takes very complex modeling to actually physically generate. It is done, but that is where only such physical tests can actually do it. Therefore, as I told you, high pressures which have to be assessed. The last one which I brought in is, because in case somebody in the audience feels I did not see any rolling of the ship, it has to do with the periods, because the periods at which the bad waves or the prevalent waves occur in that region are highly delinked from the natural roll period. Being a big ship which has a high period, 22 seconds is the roll period, and the prevalency conditions, the average period is between 8 to 12, 14 seconds. So which is why there was not so much of roll, etc. in that case. This is the last case I am going to present, because this is a unique development which we have performed and we have actually patented for it.